WAS welcomes astrophysicist Dr. Adam Frank from the University of Rochester for the first time to our free lecture series. Dr. Frank is a leading expert in the final stages of evolution for stars like the Sun, and his computational research group at the University of Rochester has developed advanced supercomputer tools for studying how stars form and how they die. A self-described evangelist of science, he is also committed to showing others the beauty and power of science and exploring the proper context of science and culture. Please welcome Dr. Adam Frank.
Hello, everybody. My pleasure to be here with you guys. So let me figure out how to start so I don't want full screen. Let's go to gallery and okay. So I'm gonna put this over to the side. Can you see can you guys see my screen? My presentation?
See you.
You don't see the presentation though?
No.
Okay, so let me share. How about now? Nope.
Also no.
Okay, so it means I got to share screen. So let's do the share screen thing. I thought I was sharing screen. Right, and we'll do this. And now we see it. Now we see it. Now we got to do it into presentation mode. All right, so I won't be able to see you guys, but there we go.
That's good.
Okay, so thank you guys very much for coming. So this is going to be a little talk about life, the search for life, and particularly intelligent life in the universe. So this is sort of my main field of study these days. I spent most of my career studying things like how stars form, how they die, planets, but in the last 10 years, I've sort of switched over to astrobiology. So the main theme of my talk is that when it comes to alien life, it's kind of time to stop giggling. You're going to see what I mean by this as we go along. But, obviously, alien, for astronomers, not for UFO heads, but for astronomers, alien life, thinking about alien life for a long time was something that just raised eyebrows. There was no science to be done. And what I want to tell you about this time is that actually that has changed considerably. So first, I'm going to give you a little history of SETI. Then I'm going to talk about the three revolutions in astrobiology. And then I'll talk about biosignatures, which is the search for what we might call dumb life. And then technosignatures, which is the search for smart life. Okay, so the first thing is this question of are we alone is really one of the oldest scientific questions that exists. You can see the ancient Greeks arguing over it. Aristotle was very firmly held that the Earth was unique and the only planet in the universe that held life, probably in some sense the only planet in the universe. It was the center of the universe. Whereas Democritus and others of his ilk argued that there were many planets and many of them had creatures just like us. As time went on, the name of this discussion changed and became what was called the many worlds debate, or the plurality of worlds debate. And you can see this is the front piece of a book, a very famous book by De Fontenelle, 1700, where every one of this was arguing that the universe is full of planetary systems. And you can see every one of these is a planetary system. By 1890, people were actually claiming to have found planets orbiting other stars, and that was important for the life debate because everybody thought that life needed planets. And so this was Thomas C., who was a very famous popular astronomer of his time, who actually ended his career by claiming that he found a planet and not giving up on that claim even after others showed he was wrong. But the beginning of modern astrobiology, the beginning of really sort of having a scientific question to deal with, starts with in 1950 with the Fermi paradox, which is the story of the Fermi paradox is Enrico Fermi and some of his buddies are at Los Alamos National Laboratories. It's 1950. They're walking to lunch and they're discussing this cartoon, which had shown up in the New Yorker, which they all got. And the joke here is that, trash cans were disappearing in New York. And so this was the cartoonist suggestion for why they were disappearing. UFOs were already a thing. And what happened was Fermi and his colleagues just started thinking about interstellar travel and its possibilities, as physicists doing little calculations in their head. And then the topic turned to something else. But about a half an hour later, Fermi, says to everybody, turns to everybody and says, where are they? Right? He had done the calculation in his head and figured out that if the universe was full, or the galaxy was full of intelligent starfaring creatures, then they should have covered the distance between the stars very quickly compared to the age of the galaxy. So why aren't they here now? Why haven't they, landed on the White House lawn and announced themselves? So the Fermi paradox became kind of a formulation that scientists began using about questions about life in the universe. The other important event in the 50s was the Miller-Urey experiment, which was this chemistry experiment where basically all the basic building blocks of the early Earth were put together. Boiling water, the gases that they thought at the time were in the atmosphere, a spark to simulate lightning. And what happened, they went away, and when they came back in this beaker was this primordial soup, as they called it, that had all the amino acids needed to make proteins. So basically it showed that, all you needed was the basic stuff on Earth, and you would get the building blocks for life, the more complex building blocks of life. So the Miller-Urey experiment made it seem like, maybe life is not that hard to form. The next big thing, which ends the decade, is Frank Drake's famous Project Ozma, which is the first true astrobiology experiment. It was an experiment to find intelligent life, but that doesn't take away from the fact it was the first time anybody did anything scientific to actually find life of any kind in the universe. And Drake pointed this telescope at two different stars and looked for signals, anomalous signals that would indicate they were of a technological origin. He didn't find anything, but he started what he was doing became very famous. Lots of newspapers covered it, and it was the beginning of SETI, the beginning of the search for extraterrestrial intelligence. So what happens next is that Drake is sort of worried about the fact that, people are laughing behind his back, but instead he gets a call from the government, which wants him to host a meeting on, of all things, interstellar communication. So he and a guy from the National Space Agency get together and they organize what's called the Green Bank Conference. And it's like 8 people, including a very young Carl Sagan, are going to come to Green Bank and they're going to talk about, this new science of interstellar communications. And the night before the meeting, Drake has to come up with an agenda for a meeting on a subject that has never been discussed before. So he sort of, his agenda is really a bunch of sub-problems that go into the main problem. And this is the beginning of what's called the Drake equation, which you may have heard of. The problem is, how many civilizations are there in the galaxy that you can talk to? If n, that number, is very large, it's going to be easy to find them. If n is very small, it's going to be hard to find them. And what Drake works out is he just puts together, a set of factors that will, each one could be studied separately. But together, when you multiply them all together, you get that number n. So the factors here are the number of stars in the galaxy, the fraction of stars that have planets, the number of planets going around these stars that are in the habitable zone. And we'll talk about that in a second. The fraction of those planets where life forms, the fraction of that life that goes on to form intelligence, the fraction of those intelligences that create civilization, and then finally, what I like to call the final factor, which is how long, on average, civilizations last. So this is the Drake equation, which has been incredibly important in structuring. It's not a physics equation. It's really a statement about our ignorance, but it helped structure how we were going to go about doing these searches. So then we get to the 70s, and, NASA and other agencies are, SETI was never funded very well, but there was at least interest from the from some of the agencies. And so, like, for example, there was this big project that the NSF was going to fund called Project Cyclops, which, as you can see here, would be hundreds of giant radio telescopes, all of the size, that radio that, in the movie Contact, the ones out in New Mexico. But what happened was SETI was then killed by the giggle factor, that sort of thing of if you try to talk about life in the universe, if you try and talk about intelligent life in the universe, for a long time people would kind of snicker behind your back. Oh, you're talking about little green men. And it was in particular William Proxmire who started this, who in 1978 awarded SETI, there was a NASA SETI program, the Golden Fleece Award, which was this idea that you were wasting taxpayers' dollars. So basically, Proxmire put in a bill that said NASA cannot fund SETI at death of SETI, and it was that killed SETI for a few years. Carl Sagan actually had to go in and convince Proxmire that it wasn't silly, but then the other over time other congressmen said, "Oh, this is a great way for me to make get political hay," and multiple times NASA found itself in the crosshairs of Congress for funding anything SETI, and that was said NASA was just like, forget it, we're not doing this anymore. So basically, from 1996 on, NASA's just like, you could not get any funding for anything involved with the search for intelligent life. Like, forget about it. If you in some of the calls for proposals, it would literally say, don't send us any proposals about the search for intelligent life. But nature and science had other plans. So now let's talk about what happened in the 90s, in the late 90s and onward, that sort of changed that story. So I call these the three revolutions of astrobiology, because when I graduated with my PhD in '92, there was no astrobiology. I mean, there were people who were thinking about it, but really astrobiology wasn't a field that had any funding for sure. And there were, you were really taking your career, you were really risking things if you're like, I want to study life in the universe. But things, as you're going to see, things have completely changed. So the first big revolution was the discovery of exoplanets. And here's a little picture of the Kepler mission, which I'm sure many of you know about. In 1995, we discovered our first planet orbiting another star. We did it via the radial velocity method, which again, I'm sure you know about. Kepler was what really blew the doors off the field by starting to discover them wholesale. And by now we know that there's 6,000 confirmed exoplanets. And in fact, pretty much every star you see in the sky, we should expect to have a family of exoplanets. And so these are just artists' rendering of all of these different kinds of worlds that are out there. But again, pretty much other than massive stars, really massive stars, we expect every star in the sky to have planets. And also, what we found is that 1 in 5 stars have planets in the habitable zone. And the habitable zone, as you may know, is the band of orbits here in green where the temperature is just right to allow for liquid water to be on the surface. If you're too close, the water will boil. If you're too far, the water will freeze. But if you're in the middle here, you will get liquid water on the surface, and we believe liquid water is important for life. So 1 in 5 planets we found are in the right place for life to form. Huge change, right? So that was revolution number 1. Revolution number 2 comes looking at this picture where I could ask you, where is this? Is this Tunisia? Is this some desert in Tunisia or in the Atacama Plains? And the answer, as many of you know, probably is no, this is Mars, right? This is Mars taken from one of the rovers. So we've now sent probes to every planet in the solar system and every type of body in the solar system, comets, asteroids, etc. So we really have learned a lot about planets and solar systems. And one of the things we've learned is climate change. You should expect climate change to happen, because here's a nice example of one. Mars was a blue world for a while. How blue, we don't know, but it's definite, that Mars had liquid water, large amounts of liquid water on its surface. May not have been oceans, but there were certainly large lakes. So, and then it lost that about 4 billion years ago. It lost its atmosphere, most of its atmosphere, and its liquid water. But as we found out last week, there's some pretty strong evidence for that Mars might have had life as well. Okay, so that's revolution number 2, the solar system. Revolution number 3 comes from studying, here's the question for you guys. Which one of these is Earth? I'll let you think about that for a second, and the answer is all of them. These are all the different faces of the Earth along its history. So the third revolution was Earth's deep history, because this is the Earth in the Hadean age, when it was very young and its surface was molten. Once the water was delivered to the Earth, most of the Earth was water. There were only sort of Australia-sized cratons, they were called. So it was really kind of a water world. There have been periods when Earth has been so hot, it's been a jungle world with almost no snow and ice on it. There's been periods when Earth was a snowball world, when it was pretty much glaciated almost all the way to the equator. Here's Earth now, yay. And in about 1.6 billion years, all of the oceans are going to boil away because of the sun's secular increase in temperature. So this revolution has taught us about how life and planets go together. So for example, here's a picture of the Archean Earth about 3 billion years ago. And it looks nice, looks like a nice place to be. You can even see these are life. These are bacterial colonies that have established themselves. But the problem with this planet is if you landed and stepped outside of your spaceship without a spacesuit, you would die instantly because you'd asphyxiate. There's no oxygen in this atmosphere. The Great Oxidation Event, as we call it, didn't occur until about 2 billion years later. This is a plot. This is time going back. This is, when the Earth formed 4 billion years ago. And this is a plot in log scale of oxygen content in the atmosphere. And you can see there was 1 million times less oxygen in the atmosphere, basically meaning there was none, until about 2.5 billion years ago. And then the oxygen level goes up, and then it goes up again to the current levels. And what did this? It was life. Basically, bacteria or microbes figured out a new kind of photosynthesis, whose one of the side effects was farting oxygen into the atmosphere. So it was all of life's activity that utterly changed the planet's atmospheric composition. And, for the creatures that were around then, that wasn't, oxygen was a poison. So they didn't fare all that well because of what they'd done. And so does that sound familiar? A species changing the planet's atmosphere in ways that may be detrimental to its own abundance? Has that happened any time that you know about? Yeah, it's happening right now with climate change, right? So what this tells you is that, life altering its planetary conditions is not unusual. It happens, right? The only question is whether or not you make it through, right? And so the question for us, obviously, is are we smart enough to deal with the fact that we're changing? Okay, so what does the exoplanet revolution change when it comes to thinking about life? Well, here's the Drake equation again. And what we find is when Drake wrote this equation, the only term that was known was this one. All these others were unknown. But here we are now, just, some decades later, and this term and that term are nailed. Absolutely, we know the values. So the fraction of planets that have life, 1. Every planet has life. The number of planets per habitable, number of planets in the habitable zone, 1/5, meaning you got to count up 5 planets, 5 stars before you get a habitable zone. So that's amazing progress towards, eventually getting N. So what does the exoplanet revolution change? We know exactly where to look, and we know exactly what to look for. And that is the next part of the talk. We're going to talk about what exactly do you have to look for. And so that leads us to the question of planetary characterization. We're never going to land on these planets, at least not in our lifetime. So how is it that we can tell anything about the planets that will teach us about life? And the answer is this planetary characterization, this process. There's theory and observational techniques that will allow you to characterize what's in the atmosphere of a planet. So here's a picture of Venus transiting the sun. And we're going to basically use this, as many of you know, this is one way that we find planets. This is a little plot of how Kepler finds planets. It finds them via transits. This is the brightness of the star, and this is time. And when the planet passes in front of the star, we now have detectors that are so sensitive, it can see the little teeny tiny drop in the light output as the planet passes in front of the star. right? So it's basically this technique. But now what we're doing is we have, oh, there it is again. We have our telescopes, and the detectors are so powerful that we can also see this veil of gas, the atmosphere. We can track the light from the star as it passes through the veil of gases. And we can do spectroscopy on that, which I think you guys all know what spectroscopy is, to be able to characterize what's in the atmosphere. What is the atmosphere made of? Is it oxygen? Is it nitrogen? Is it carbon dioxide? So, how do you do that? Well, here's a star, here's a planet, here's the starlight passing through the veil of gases. And as you all know from doing spectra, the light that passes through the atmosphere will get absorbed. Different wavelengths get absorbed in different ways, and that leaves an imprint in the spectra of the compounds in the atmosphere. So all these lines here, for example, are titanium oxide. These lines here are water. These lines here are also water. So this fingerprint, there's going to be fingerprints in the spectra that are going to tell you what's in the atmosphere. So you may think like, we've been doing spectra for a long time, but to be able to get the spectra that comes from that just, those few photons that are passing through the atmosphere of the planet, that is what's really amazing. That's really where the technology has advanced. So this leads us now to the idea of biosignatures. So the idea is that future space telescopes should be able to detect things like carbon dioxide, methane, and oxygen in an exoplanet atmosphere. And it's that combination, because of the chemistry, that could be a sign of possible life. So a biosignature, an atmospheric biosignature, is going to be something that wouldn't be in the atmosphere if life didn't put it there. For example, oxygen, right? So if we go back, here, right? If you looked at Earth back here, you would not see any oxygen in the atmosphere. If you looked at Earth here and here, you would see oxygen in the atmosphere. So oxygen becomes a biosignature. Oxygen tells you, if you see oxygen in the atmosphere, it tells you there's a biosphere there, right? Biosphere. Biospheres can produce biosignatures. It's also possible, depending on the biosphere, how robust it is, etc., that it won't produce any biosignatures. But the hope is, like Earth, that a vibrant biosphere, a biosphere that's consuming a lot of energy, i.e. from the solar radiation, or stellar radiation, is going to produce lots of things in the atmosphere that will be detectable from a distance. Okay, so that's what we mean by biosignatures, and we're gaining the capacity to find them. That is what is amazing. So just to find a point on it, here is, if you were looking at Venus, if you were doing a spectra of Venus, and if if Venus passed in front of the sun, and you were looking at the absorption spectra of Venus, what you'd find is a nice big dip for CO2, right? So you'd be like, oh, there's definitely CO2 on Venus. And if you did it for Mars down here, you'd get the exact same thing. Yes, here is a clear indication that Mars has a CO2 atmosphere. Notice you see these both, even though Venus has a whole lot more atmosphere than Mars does. Now, if you looked at Earth, what would you see? Look, you'd see an abundance of water lines, and you'd also see ozone, oxygen 3. This would tell you that Earth was a living world, right? And it's the combination, actually, there's other stuff here, methane, other things, that when you do the chemistry, you figure out that, wait a minute, if there wasn't life on this planet, then these lines, after, a few 100,000 years, that these lines would go away because the oxygen would all get bound up in rocks, right? So it's really this line here, this ozone line, that really tells you Earth is a planet that hosts a biosphere. It is a living world. So the other thing we can do is we can look at biosignatures through time, right? We don't know when we're going to see planets. Depending on the star's age, that will determine the planet's age, and planets change, as we've seen over time. So we can ask how The various gases on Earth, for example, have changed over time. So down here on this axis, I'm showing you the abundance. It's called column S, but it's really the abundance. This side, the right side, is lots of that kind of gas, a little bit of that gas. And so this is time, right? That's 4 billion years ago. So what do you see? 4 billion years ago, there was lots of carbon dioxide and lots of methane and almost no oxygen, as we talked about, right? We've already seen this. But as time goes on, right, you get the great oxidation event. The oxygen eats up the methane. The carbon dioxide gets locked up in various forms. And so by 1.5 billion years ago, there's still methane, but not a whole lot. And oxygen is pretty rich. There's lots of oxygen. And then by about 500 million years ago, you start getting ozone, right? This is the modern Earth. But so let's look at this, what the spectra actually look like. So in the Archean Earth, it may be that there was, we don't know whether the Archean Earth may have been a haze ball. Like if you went into orbit around the Archean Earth, you may not have been able to see surface features because of there might have been a really thick haze. We don't know. But either way, you can see like there's lots of methane lines, there's lots of water lines. So you'd say this is an interesting planet. There's an ocean there, but you wouldn't see any evidence necessarily of life. When you get to the Proterozoic Earth, where you have 1% of the total level of O2, or this is either 1% or 0.1%, what you see is if you have 1%, then you get this strong ozone line, right? But then there's still the water lines, etc. So it's the ozone line that tells you like, oh, now we can detect the biosphere. There was a biosphere up here in the Archean, we just couldn't see it. And then modern Earth, there's the strong O3 line. There's lots of other stuff that will tell you that Earth has a biosphere. One of the interesting things as we do this studies is that we're going to have to deal with the fact that lots of planets we think are going to be ocean worlds. Earth is very weird that we've got about approximately half water and half continents. In general, since the water is delivered by comets, you would expect to either have so much water that you fill up everything past the highest mountain, or everything would be all mountains would be underwater, or you wouldn't get enough water to do anything more than have some lakes. So either you should be, a water world, or you should be Arrakis, Dune, for you science fiction fans. So the question is, what will planets like this be able to form life, and will they have biospheres on them that are detectable? Okay, just to show you the state of the art right now, here is a spectra from the James Webb Space Telescope. The dots are the actual data. The blue lines are a model fit. And what this shows is, so this is wavelength. This is the amount of light blocked. So you're basically seeing these dips are the absorption spectra. And what you see is methane. You see lines associated with methane. You see lines associated with carbon dioxide. And these lines for methane and carbon dioxide are so well characterized that we can say for sure they're there. Not only can we say for sure they're there, but this mix of methane and carbon dioxide tells us probably that this is a water world, that this planet K2-18b is a world of immense amounts of water. Now, this is not an Earth-like planet at all. This is a planet that's 8 times the mass of Earth, what we'd call a sub-Neptune. So this is an entirely new class of planet, what we call a Hayacean world, hydrogen ocean world. It's got a hydrogen atmosphere and then an ocean below it. There's still debate about it, about whether that's what this is, but it's a very interesting, intriguing possibility, and this data support its existence. Now, over here you see dimethyl sulfide. You guys may have read about this. In this paper, they said like, well, we see a little wiggle around where dimethyl sulfide is. Dimethyl sulfide is on Earth is produced by phytoplankton. This is on Earth. This is a definite signal of life on Earth. Then a paper was published just a few in the summer, I think it was, where they were like, "Oh, we really think we don't." They didn't say we say they said we now see even better evidence for dimethyl sulfide. I think most of us were like, "Meh, not really." But what was amazing was finally reached a point where they'd done a reasonable job. It was a reasonable piece of science, and now we could argue about it. Whereas beforehand, 20 years ago, there was nothing to argue about. There was no data. Now we actually had data to argue about. So the James Webb Space Telescope is just on the hairy edge of having the capacities to do this. I don't expect, unless we're lucky, that JWST will find biosignatures, but maybe we'll get lucky. Okay, so now let's talk about technosignatures, which are signatures of an intelligent technological society. So here, if you pulled up to Earth, this is the Earth at night, you would immediately recognize that Earth had a technological civilization because of the lights, right? You know, our cities and roads are lit up at night. It's clear that we are harvesting energy for our technological civilization. So, you know, this is an example of a technosignature. Now, there's like a biosignature. Now, could you see these across interstellar distances? The answer is yes, if you had a lot more light. So if you had a planet that was, here's the word of the day, an ecumenopolis, meaning a city planet like Trantor from the Foundation, hopefully some of you are science fiction fans, or Coruscant from Star Wars, then, you know, that would produce a lot more light. It's a lot more city than Earth. And it turns out, this is a study done by Thomas Beatty. This is distance and urbanization factor. Blue is highly detectable. So it turns out that if you have a city that is highly detectable, then with like future, you know, space missions that we've thought about building, yeah, you would be able to detect city lights. You know, you wouldn't be able to detect anything here. This is distance, by the way. So out to about 5 parsecs, or even if you could get to the blue, if you could out even to 10 parsecs for planets that had lots of city lights, you would be able to detect them with the next generation of space telescope. The other thing that we'd be interested in finding our other example of technospheres are what might be called megastructures, things like Dyson spheres, where a civilization, you know, builds giant solar collectors orbiting their star to collect all the energy from the star. And there was already an example where somebody thought they'd found something like this. Bajoyan star it was called, and here's the transit record of the Bajoyan star. You remember a planet is supposed to look like this, nice and smooth and repeatable, and Bajoyan star was just having these crazy sharp dips that were coming and going. And for a while, people, you know, it was at least suggested like, hey, maybe these are megastructures orbiting the star. Turns out they were gas clouds or dust clouds. Wah, wah, wah. But it was like one of the first times people were like, oh, okay, we have to take the possibility of a technosignature seriously. Another possibility for a technosignature is seeing terraforming. Terraforming is the idea that you could take a dead planet and modify it, you know, using kind of like planetary scale engineering to turn it into a living world. So you might have these giant atmospheric reactors that are belching out chemicals that could warm the planet up and give it an atmosphere. So this is something that we might be able to detect. And what kind of gases would you use to warm up a planet? Ironically, it would be chlorofluorocarbons, the things that we had to ban because they were eating our atmosphere. But it turns out that chlorofluorocarbons, or CFCs, are great greenhouse gases. And in fact, we showed in a paper a few years ago that if you had a planet, here's a planet with, this is a climate model for a planet. This is the whole planet. You're seeing the, you know, the whole disk, or the whole sphere at once with 1 times Earth chlorofluorocarbons, 10 times, 100 times. The question here is what this is showing is how hot the planet gets. And you can see if you have 100 times chlorofluorocarbons as the Earth does, yeah, the planet's going to get a lot warmer. But the main thing we're interested in here is that this is a spectra, and these lines here, these are chlorofluorocarbon lines. These are lines that come from chlorofluorocarbons. And you can see that even for 10 times Earth levels chlorofluorocarbons, it really stands out, these red spikes. So even with the JWST, you would be able to find these. So it's a nice example of a technosignature. If somebody is using chlorofluorocarbons to do something with a large scale, we would be able to detect them tomorrow if we could find them. Okay. So getting towards the end here. So the best thing about all of this is that this search for extraterrestrial intelligence, be it smart biosignatures, meaning dumb life, or technosignatures, meaning smart life, is finally getting going. Okay, so every 10 years, astronomers get together and they produce what's called a decadal survey, where they, get together and they decide as a group what should NASA spend its money on, right? What should, when NASA was actually spending money on space probes before what happened, the disaster that's happening now, what should NASA spend its money on? And here was one of the one of the three things they chose was worlds and suns in context. They were saying pathways to habitable worlds. They were telling NASA and the European Space Agency and everybody else, build us a giant telescope that can do biosignatures and find life. So that shows you that the entire astronomical community now thinks this is one of the most important, if not the most important problem for the next 20 years. All right, just to conclude, I want to note, we've all heard of I just told you about the Fermi paradox. I want to note that there's actually two versions of the Fermi paradox. One is, why aren't they here now? But you'll also hear people say well, we've been searching for life for, many years and we've never found it, so it's not out there. But it turns out that's just not true. And the reason is, for the most mundane reasons, is money. SETI was never funded. There was never really any money for SETI. So people just did it on their own. They had an hour left of observing time one night, so they pointed the radio telescope somewhere and looked for signals. So Jason Wright, a colleague of mine, he did a study where they counted up all the SETI searches that have ever been done. And if you think of the night sky as the ocean that you have to search, how much of the ocean have we searched? And it turns out it's a bathtub. Right? So if you were looking for fish and you pulled up a bathtub worth of ocean and there were no fish in it, would you then say I guess there's no fish in the ocean? So there is no indirect Fermi paradox. We call this the indirect Fermi paradox. There is none. We just never looked. But now we're starting to look. Okay, finally, what will they look like? What will aliens look like, right? You guys have all seen science fiction movies, I'm sure. Will they just be like weird bacteria or weird creatures, like this, or techno or whatever, alien dinosaurs, or this guy from, was this Alien Covenant? I'm not sure which movie this was. This was one of the recent alien movies, which was really dumb. This is the thing that the guy stuck his finger in. It's don't do that. Or will they look like this, right? And the answer is probably not like this, right? Evolution is a mix of convergence and contingency. Contingency is accidents, and convergence is kind of, evolution finding the same solution to the same problems. And so, while you might get jointed sticks, like this to move around with, the idea that you're going to get this same body plan with two eyes on a shoulder and mouth on a shoulder, highly, highly unlikely. We are most likely the only humanoids in the universe, or at least certainly in the galaxy. Okay, so finally UFOs, because everybody, wants to talk about UFOs. Here's the thing I did for the New York Times. I'm a physicist who searches for aliens. UFOs don't impress me. My main reason here is that, I think there should be an open, scientific, transparent investigation of UFOs and UAPs. But there is no data of the kind that I would need, of the quality I would need to be able to tell my colleagues I found alien life on an alien planet, that would tell you that UFOs and UAPs have anything to do with non-human technology. There just isn't. I mean, and they're just, you can run through it. You can't use personal testimony, even of pilots who are, God bless the pilots. I think it's great that they have freedom to tell what they've seen, but personal testimony is the worst form of data. So you need to have instrumental data, and you need to be able to control your instruments, and that just doesn't exist. Those videos are blurry blobs that you don't know where, you don't know anything about the cameras that took the pictures. You don't know when the last time they were refurbished, et cetera, et cetera. It's all pre-digested videos that are leaked, so you don't know anything about them. So, okay, so that's where I stand on UFOs. But I'm all for, let's have an open scientific investigation of them. Okay, sort of why all this matters. Well, I think for everybody in this room, we all know why it matters. We're really interested. But also, that last factor in the Drake equation is the lifetime of civilizations. And, looking for technosignatures is kind of if we found some, would tell us something about how long civilizations last. We don't know whether or not the universe does long-term civilizations. It may be that every civilization that forms, if they form, lasts about 200 years before they wipe themselves out in one way or the other. And how long have we been around? Oh, about 200 years as a technological civilization. So this bears very relevant on questions that on questions of where we are now in this moment in history. Okay, so the future is this thing called the Habitable Worlds Observatory. It's what that report I was talking about, that decadal survey, said, please, NASA, go build. And, right now, unfortunately, with what's happening with NASA, I'm a little skeptical that NASA is going to be the one that builds it unless something changes. But somebody's going to build it, whether it's the European Space Agency or China, which has expressed a lot of interest in this. But hopefully somebody's going to build this. I hope it's America. But this is the future, and hopefully within 20 years we'll have a telescope that is designed to find life. Okay, so I'm gonna stop this and say thank you. I have to always have pictures of Carl Sagan because Carl Sagan was the hero of this whole field. There's like no part of this story that Carl Sagan doesn't show up, even like in the background. So anyway, thank you very much. And I'll stop sharing.
All right, anybody have any questions? Surely somebody has questions.
Let me ask one. If life started on our planet under the ocean, and we know there are oceans in some of our satellites around different planets, you wouldn't detect that in the atmosphere of those planets.
No, because they have no atmosphere, right? Titan is a really interesting example. Titan has an atmosphere. Titan has liquid. It's the only planet that has open surface liquid, but it just happens to be methane, liquid methane. But you're right about that. The really interesting places for life in the solar system is not Mars, though Mars is interesting. It's Europa and Enceladus, where these underground or under ice oceans. Europa has twice as much water on it than Earth does. That is phenomenal. But it's under 10 meters. That ocean, the 60 meter or kilometer, 60 kilometer, or maybe it's mile, 60 mile deep ocean is under like 10 miles of ice. So, we've got to be really clever to figure out how we're going to tell whether or not there's life down there. So it's interesting that the water does bubble up. It gets frozen when it gets up because it's like basically the ice is like, icebergs that are crushing against each other. And the fissures, it seems like you may get slow upwelling from deep down. And so one idea is just to look at the chemical compounds in that, the ice that's right at the fissures, and maybe that'll tell us something.
Well, but Enceladus blows it up 1,000 feet, right? You got water geysers.
Yeah, and Enceladus, right? And people have flown, right? They flew the Cassini probe through those geysers, and they found that it was brine. It was like salt water. So that was super. That was super interesting.
And I didn't know that. It actually flew through a geyser?
It flew. They piloted it through the geysers from Enceladus.
Yeah.
I know. And the problem is that it wasn't built for that. There weren't the kind of detectors on Cassini to really help you answer the question. So now I think some of the things that are being sent now are going to have probes. They're going to purposely send them again and again through the geysers to sort of figure out what the water's there. I love this. Steve Labkoff. Yes, all these worlds are yours except Europa. Attempt no landing there. Yes, 2010, right?
Don't land there. Big trouble. What about other civilizations that likely that they can find us?
Yeah, well, we've been visible with technosignatures since the Great Oxidation Event. So yeah, for sure, somebody looking at us will have known that we have biosignatures. Which is why, yeah, maybe there are, there's a whole thing of solar system SETI or solar, artifact technosignatures where like maybe we should, because like looking on Earth, because the whole thing is when did they arrive? Like maybe they visited a billion years ago, right? And then or sent probes a billion years ago. So the question is, where would you look? So you don't want to look on Earth because everything gets eroded, but the moon or certain kinds of orbits, those might be good places to look for artifacts, um, dead space probes that were sent across space and time.
Because it's the factor of the distance is very important, right? Because I mean, the distances.
That's what it is. The distances, and can you travel faster than the speed of light? I don't know. I mean, the laws of physics are pretty harsh about that, and so if you can't travel faster than the speed of light, then the distances, interstellar travel may be very expensive in terms of energy and very difficult. And maybe it's like not done very often, right? So there's it's a very interesting thing to consider if we have that much of a handle on the laws of physics that we're not going to have warp drives, then yeah, solar systems could be vibrant and active, but interstellar civilizations just don't make sense. If it takes 300 years to send a message and get it back, like how does diplomacy work, right? If it takes 300 years to send a message saying, we don't want to go to war with you, and then it goes and it comes back and they're like, okay, it's been 300 years, everybody's dead,
As far as like a binary life form and like basically computer life where you can have a lifespan that's a lot longer.
Yeah.
What would the computer want to do? Would they want to spread some bacteria? I don't know. But that's the only way I could see the travel anywhere. And then what would you be looking for? You'd be looking for something that's probably not pond scum. They'd be looking for some sort of rare chemicals.
Well, if they're communicating, let's say there are, because people have thought about this a lot about, the possibility that the first life you detect is not life, but is digital, in some form. It's machines, maybe living machines, right? Could be conscious and sentient, but, they would still communicate with each other. So, you'd look for tight beam, they'd still have to communicate by using radio or laser, so then you'd be looking for their propulsion signatures or their, other things that they would produce in their metabolism, so to speak.
Got a question from one of our online people, from Claire. She asks, what's your view on the growth of commercial space exploration? Do you see it as a positive in that it may provide additional needed funding for astrobiology research? Do you see it as a hindrance that may taint data and possibly disrupt abilities to detect possible biosignatures and tech signatures coming from other solar systems?
I have always been a huge fan of commercial space program. I think, I absolutely believe that should we be able to make it through the next century, which I think is going to have some considerable challenges like climate change, but there's also AI and nuclear war, which is, still around. But if we make it through, then the solar system is the prize we win, right? And I could imagine that in 1,000 years, we have a fully settled solar system where, not only, Mars and other, every nook and cranny, but that also, I've written on this, we did some research on this, on orbiting space stations, orbiting space habitats with millions of people living on them. That is, you use asteroids, you can either hollow out the asteroids or like the Expanse, my ship back here, or other things. So, really especially if there is no warp drive, then really the next 10,000 years or whatever of human history is the solar system. But that being said, where we are right now, I don't see commercial space having anything for, commercial space is interested in commerce, so that's not their vibe, right? They are really interested in making money, which is fine, from space ventures. I'll say that, Elon Musk, I used to be very excited about everything Elon Musk did, and now I'm just bummed. I can't get excited because, you've been hearing me talking about the devastation that is happening to NASA, and that's Elon Musk. Elon Musk drove that, and so and then all the other stuff, the Nazi salute. Sorry, it's hard for me to get behind a guy who is. Who is I respect SpaceX. SpaceX is amazing, but he's the face of SpaceX, so it's hard to pretend he didn't do that. So that kind of you know, what can I say about that? But that has sort of tainted. I'm hoping somebody else. There's lots of there because it's space commercial space venture. There's a lot of players, and it's not just the billionaires, right? It would be great actually to get away from these billionaires who, it's kind of single-handedly are dominating things. There's Stoke Space, which has built these really interesting engines. There's a company that wants to launch. You couldn't do a human launch with this, but using a giant centrifuge, they spin these things up to like 38,000 kilometers per second and boom, punch them out. And you can get almost all to the edge of space, and then the rocket motor turns on. So, commercial space is great. It's just we need more players, and it would be good if we didn't have people who made Nazi salutes. Yeah, as the leaders.
You tell us a little bit about your book.
Yes.
Please tell us something about your book, Little Book of Aliens.
Oh, it's, what I'm trying to do is the book is about everything about aliens. It's got a little bit of the history that I sort of showed you. I talk about UFOs because so many people are interested in it. I wanted to introduce people to sort of like the history of UFOs. I had to do that research myself, because I hadn't really, it's not something I followed. And then sort of, what the problems are with UFOs. And if you really wanted to do a real scientific, exploration of UFOs, what it would have to look like. And then the rest of the book is biosignatures and technosignatures. The thing I wanted to convince people of and show them was that we're that close. Like in the next 10, 20, or 30 years, we will have data. We will have data will be relevant to this question. I can't tell you what the data is going to say, but I can say for sure that we're going to have data. So, it's been 2,500 years of people and their opinions, and now finally we're going to have actual factual data, and that data is going to tell us something about life in the universe. So that's really the point of the book. It's a little because it's thin. I wanted to keep it, accessible and fun. But that's really what the book is about, is like, holy crap, we're finally there in answering this question.
Thank you.
Related question.
Do you think the Vera Rubin Observatory or some of these giant observatories that do large sky surveys have spectroscopy abilities that could cover a large swath of sky and look for signatures in planets?
Yeah, I don't think the Rubin telescope is not really there's things it can do, but not really exoplanet characterization. The kind of spectroscopy you need to do to get like I was saying, to be able to detect oxygen. It doesn't have those capabilities. It'll do other very interesting things, but it's not a great. There's parts of the technology though that I think will be useful. I like the coronagraph and things, but it's not really an exoplanet or characterizer.
I didn't know if that one could do
Planetary transits, if it had that kind of resolution, I guess.
I'm not sure of it, but it's whatever it doesn't have the accuracy to be able to do the atmospheric characterization.
Gotcha.
Being under the atmosphere, you see all the
As noted, it's also within our atmosphere, which kind of makes finding those signatures a little difficult.
Somebody mentions here, Claire, you mentioned in graduate school in the 90s, astrobiology didn't exist. Did you personally always believe in the legitimacy of the search for ET? One of my professors, one of my mentors was a guy named Woody Sullivan, who I loved, who did SETI. He was one of the few guys doing SETI, the only guy in my department, the University of Washington, Seattle, who was doing it. And I loved talking to him. I always thought SETI was worthwhile doing. I didn't want to do it because for a couple of reasons. One, it was career death. You only did SETI if you were unbelievably brave or you were already tenured, right? But I also, at the time, the kind of, radio SETI really requires, for technical reasons, requires that somebody is sending you a message. Somebody's taken a giant transmitter, pointed it right at you, and is announcing their presence. And that was a little too anthropomorphic. Like, why would anybody do that? It was too much like, they know that we know that they know that we know that they know that we know that we're going to send them a message. Whereas the modern, the transit stuff and the atmospheric characterization, it's much more like you're a detective, staking out a building. You're sitting there in your car with your cold cup of coffee and your crappy donuts, and you're just watching. You're just watching to see, whether there's a civilization going about its civilization business. So it's an entirely different approach. So at the time in the late 90s or early 90s, I believed it was worthwhile, but I didn't believe in that approach.
What is SETI doing now? How they changed?
Well, SETI, in some sense, SETI, radio SETI, what we usually think of SETI, is now, for me, under the umbrella of technosignatures. There's now many, many ways to search for signatures of intelligent life. And the classic radio SETI, the thing that, you guys, I'm sure everybody's here watched Contact, that's just one form. So it's still going on. And now what the advance is, excuse me, machine learning. You can now look at a squazillion channels, radio channels, and just have the computer search for anomalies. So the amount of data that you can swallow now is exponentially large, and you can have artificial intelligence search for the thing that you're looking for.
How many exoplanets have they found oxygen signatures on?
Zero.
There's zero, right? Yeah.
Yeah. So we haven't found any biosignatures. So.
Got a question online. What do you think about 3i Atlas? What are the chances of it being artificial?
Zero. Pretty much zero. Avi Loeb, I wish Avi Loeb had a little deeper sense of responsibility in what he does, I know Avi. Avi is a wonderful person, very generous, very, and a great has been a great scientist. But I don't know, man. His thing with many of us are very saddened by what Avi does now because, he's trying to say like, oh, I'm just proposing the possibility, but he's in the limelight. He should understand that he's in the limelight, and anything he says on his blog, which is not a published scientific paper, gets picked up by news all around the world. Harvard professor says, this thing could be aliens. 3i Atlas was a comet. You could tell it was a comet. It's a cool new comet. It's got some things that are unusual, of course, because it's a comet from another solar system. Thank God it's got some unusual stuff. But, you got to really stretch it to say like, oh, these things that we're seeing that we don't understand are aliens. And it's just like, it does a great disservice to this field, like where, we're trying to be responsible. I'm here talking to you guys. I'm telling you like how we'll know when we'll know, because everybody wants to know. The first line of my book is everybody loves aliens. So as scientists involved in this, we got to really be respectful of our, the audience that's paying for our research, and not, give them a bunch of stories that, are titillating. There's really exciting stuff happening now, and it's going to take time, and I'll be the first one. These ISOs, these interstellar objects, absolutely, we may find one is an artifact. Rendezvous with Rama. Has everybody raised your hand if you read Rendezvous with Rama, Clark's book? Yeah, so good. Everybody. Okay, see there. You guys should all go home and get Rendezvous with Rama by Arthur C. Clarke, which was written in the 70s. So good. So good. So, I pray that one day something that's an artifact comes through. But, making up stories or just, extrapolating wildly in public is really not good. That's my...
What do you think of Oumuamua?
Same thing, Oumuamua was the first one. It was super exciting, and that was like the beginning of sort of Professor Loeb, sort of like a pit bull latching on to something and not letting go. And the worst part of this was that, there were lots of, Professor Loeb is not a guy who's worked in comet studies his whole life, right? He's an astronomer, but most of his career was in studying black holes, early universe, so like, I don't know anything about comets. I can read some papers about comets and begin to work in the field, but it takes literally decades to become a true expert on them. And the people who were comet experts, like Steve Desch, were like, what are you saying? Professor Loeb was making these claims about what comets can and can't be or can and can't do. And they were like, that's not true. Or that there's a much better explanation that doesn't involve an alien artifact. So Oumuamua was most likely a comet. We have good, reason to think it was a comet, but it left so early that we didn't have, great data, and it didn't come close enough for like the coma to form. And now, 3i Atlas is behaving exactly like you'd expect it to behave if it was a comet, which is so exciting. That's the other bummer, right? So we're all arguing about, is it an alien spaceship? No, it's a comet, but holy crap, it's an alien comet, right? It's a comet from another solar system. Can we just spend some time freaking out about how awesome that is instead of arguing about whether it's an alien artifact when it's not?
Follow up from Claire, it's in the chat. If we did discover alien civilizations and an ability to make contact with intelligent alien life, what do you think the best diplomatic approach would be, or the most pragmatic for us on Earth?
10 days.
We should send Dwayne "The Rock" Johnson, right? He would be, as far as I'm concerned, like, right? Somebody asked me this one time. I was on Ira Flato on Science Friday, said, who should we send? And I was like, without doubt, Dwayne "The Rock" Johnson, because, he's good looking, he's very kind, and he's also big. So I think that would communicate everything we need to do. If we did discover one, contact is such an interesting thing because we sort of have this idea of like, oh, well, this was Sagan things. We'll teach them math. Like, how would we even talk to them? How do we even know that their minds are structured like our minds so that language, would be possible? Communication would be possible. And, it was always Sagan's thing like, well, the laws of math are universal. So we'll start with 1 + 1 = 2. And then we'll, build our way up. And then sooner or later we'll be, exchanging knock-knock jokes and cures for cancer. But, the movie Arrival, I love. You should really watch the movie Arrival because it really shows you how that, they send two people in. One is kind of Carl Sagan, another one is a linguist. And the Carl Sagan fails miserably. Like, it just doesn't work. Like, math is not a universal language. But it's the linguist who understands that language is embodied. It requires you to have a certain kind of body and a certain kind of mind. And she's the one who figures out how to communicate. So I think even that idea of communication is tenuous. Probably one more question and then I'm going to have to roll because I got to get up early in the morning.
Yep. One last one online. Should tidally locked planets and habitable zones be disregarded as low probability locales in the search for life?
This is a killer question. Yeah, right. So most of our effort is going into M dwarf stars because they are the most numerous. Right? The Earth is the sun is not the most common kind of star. The sun is not an average star. It's in fact quite a bit larger than the average star. And the problem is most stars are M dwarf, cool, small stars that have habitable zones that are very close in, like literally on 4 or 5 day orbit or week-long orbits. And there's a lot of reason to believe that those are terrible places for life. And yet we're investing all of our efforts into looking at those planets. And so there's just a paper by David Kipping, who you guys should all follow David Kipping's Cool Worlds podcast or videos. He does great videos. And he just wrote a paper that did what's called a Bayesian analysis and said, listen, if there's life on M dwarf worlds, why aren't we orbiting an M dwarf world? Because you'd expect if you just pulled life out of, pulled a habitable planet out of a bag, most inhabited planets would be around M dwarf stars. So we should, on average, find ourselves around an M dwarf. We don't. We find ourselves around a G yellow star. So yeah, it may be a really bad idea, but we don't know. So
Thank you.
All right. Thank you. Let's wrap it up.
It was a pleasure talking to you guys. It's always great to see the work you guys are doing. It's really nice. Astronomy is really unusual to have such dedicated amateur, people who are doing the science themselves. It's really great. So congratulations to you guys.
Thank you.
Bye.
Good night.